In the previous lecture, we have discussed about the first law of thermodynamics, thermodynamics introduction, second law of thermodynamics, and entropy. In this lecture, we are interested to deal with the thermodynamic relation. We had introduced the concept of Maxwell's relation from the first principle. We apply this to the discussion of phase transition, and we will explain the anomalous expansion of water in the range 0 degree centigrade to 4 degree centigrade, and then we are interested to explain the TDS equation, and from the TDS equation we get the heat capacity equation. From Maxwell's relation also we get heat capacity equation. We will explain this term separately in the forward discussion. Okay, now we will first discuss about the importance of thermodynamic relation and what is the necessity of this relation in the context of thermodynamics. Now if we explain this, we have deal with the terms many thermodynamic properties: temperature, pressure, volume. Among these, the two important properties are internal energy and entropy. These two are very important. Why? As because these properties cannot be measured in the laboratory directly. So you will ask me, then how can we measure these properties? I will give you the answer that to solve this problem, we require the thermodynamic relation. Now what is the relation we will discuss later. So here lies the necessity of the thermodynamic relation. The thermodynamic relation contains some partial differentiation of some intensive and extensive thermodynamic properties. Now the partial differentiation relation is very large, but only 4 of them are very important, and these are fundamental. These 4 partial derivative equations are Maxwell's relation. We will discuss this. Okay. So the necessity of thermodynamic relation is lies in this context. It is very important, and it is the building blocks of thermodynamics. It helps us to solve many problems in thermodynamics. So let's start from the derivation of Maxwell's relation. I have discussed the importance of thermodynamic relation and the necessity of thermodynamic relation. Now I want to describe the 2 important partial differentiation theorem or properties. The first, del z del x so 1 by of del x del z. Okay. At constant y. If we consider x, y, z with 3 variables connected by the equation f of x, y, z is equal to 0, then we will get del z del x, that is the partial differentiation of z with respect to x at constant y is equal to 1 by del x del z, that is partial differentiation of x with respect to z at constant y. This, and 2 del x del y at constant z into del y del z at constant x into del z del x at constant y will be equal to minus of 1. These are the two important properties of a partial differentiation equation which holds for f x y z is equal to 0. Now we will prove this. Okay. At first, to prove this, we have f of x y z is equal to 0. Okay. Now from this we can write x in terms of two independent variable. Here one variable can be expressed in terms of other two independent variable. That is, I want to say x can be expressed as a function of y and z, and z can be expressed as a function of x and y. This. Now from this we can write dx will be equal to del x del y at constant z into dy plus del x del z at constant y into dz. This, and from this we can write dz is equal del z del x at constant y into dx, del z del y at constant x dy. Okay. Now we will put the value of dz. We will put the value of dz in the previous equation here. So by putting these, we get dx is equal some del x del y at constant z dy plus del x del z at constant y into dz, del z del x at constant y dx plus del z del y at constant x into dy. Now equating the coefficient of dx, this will be the coefficient of dx on the right hand side, and this will be the coefficient of dx here is 1. So by equating the coefficient of dx, we get 1 is equal sum del x del z at constant y into del z del x at constant y. So from this we can get del z del x at constant y will be equal to 1 by del x del z at constant y. This is the first property we discussed in the previous section. Okay, this is proof. Now the second property lies from these. Second property can also be get from this equation. Second property is equal to del x del y at constant z into del y del z at constant x into del z del x at constant y is equal 1 or minus 1. Okay. So to prove this, we equate the coefficient of dy from this. Coefficient of dy. Okay, this is the previous line. Okay. Coefficient of dy. Oh. Now equating the coefficient of dy from this equation, we get this, and this is the reciprocal. If we get the minus 1 by of some reciprocal from this theorem, and we get the final answer is this. So the two property of the partial differentiation is proved here. Now we will derive the Maxwell's relation. Applying these two properties, we will derive the Maxwell's relation. Maxwell's thermodynamic relation. Thermodynamic relation. Now, what is the importance of Maxwell's thermodynamic relation? Maxwell's thermodynamic relation constitute the general thermodynamic theorem applicable to simple homogeneous system. It may be solid, liquid or gas. Now to derive this, we will combine from the combination of first and second law, we will derive this. How can we derive? From the first law we get dq is equals of du plus pdv for hydrostatic system, and from the second law we get dq is equal tds. All the terms are known to us if we read carefully the first and second law of thermodynamics. So from combination of the two law we get tds is equals some du plus pdv for hydrostatic system. T is the T is the temperature, absolute temperature, temperature in Kelvin scale. ds is the entropy change, du is the internal energy change, and dv is the volume change, p is the pressure. Okay, now we here consider each of these variables dependent on two independent variables x and y. Sorry, if we explain this in another words, these variables or these thermodynamic parameters are depends on two independent variable x and y, that is the function of x and y. So we can write t as a function of x comma y, ds as a function of x comma y, du as a function of x comma y, p as a function of x comma y, dv as a function of x comma y. So if we break this equation we get t ds, from ds we get del s, okay, del x at constant y plus t into del s del y at constant x. This is equal del u del x at constant y plus del u del y at constant x plus p into del v del x at constant y plus p into del v del y at constant x. This is our this is our main equation. Now from this, here x and y are the independent variable, so dx and dy, sorry, there is a large mistake. Del x into dx, del y into dy, okay, into dx into dy into dx into dy. Okay, now we are interested. Here x and y are the independent variables, so dx and dy are the independent variation. Okay, now we will equate the coefficient of dx and dy separately. So by equating this we get t del s del x at constant y is equal dx del u del x at constant y plus this is du e into x constant 1. Okay, t into del s del y constant x del u del y constant x del v del y constant x. Okay, these two equations we get, we number these equation. This is equation number 1, this is equation number 2, this is equation number 3. So from this, if we differentiate 2 with respect to x and differentiate 3 with respect to y, and subtracting this and rearranging, we can get okay, subtracting this and rearranging, we can get what we get. We get del t del y at constant x del s del x constant y. Okay, this subtraction is done, plus some del t del x constant y del s del y constant x is equal. Now these two terms cancel each other, and we get only this term and this term. So minus of del p del p del y constant x del v del x at constant y plus some del p del x at constant y del v del y constant x. This is expressed in suitable form, in Jacobian form. This can be expressed in Jacobian form. We can write this as del of t s del of x y is equal del of p v del of x y. This is a Jacobian representation of the above equation. This is the equation number 4, this is the equation number 4, and this is the equation number 5. So now if we explain, break the Jacobian term, we will get del t del x del t del y del s del x del s del y. This is equal del p del x del p del y del v del x del v del y del t del s minus this. Okay, this is the determinant expression of this. now if first relation is obtained, if we put x is equal sum t and y is equal v, then 5 number equation, this, I think this is the 5 number equation. I got erased. Okay, if we put this, we get from 5 we get del S del V at T is equal del P del T at V. This is the Maxwell first equation. Equation number 6. Equation number 6. Okay. Second relation. Okay. Del S del P, I think. Del S del P by constant T is equal minus of some del V del T constant P. This is, I think, second relation. Maxwell's second relation. Third relation is obtained by interchanging of S and T. So this, okay. Del T del V at constant S minus of del P del S at constant V. Okay. This is the third relation, and the fourth relation is obtained del S del P, del S del P. Fourth relation is obtained by del T del P constant S is equal some del V del S and constant P. This is the fourth relation. And equation number 9. These are the Maxwell's four relations, which are the building blocks of the thermodynamics. From these four equations, we can solve any problems in thermodynamics. These are very important. So, this is our first lecture for thermodynamic relation. In the next lecture, we will discuss about the important Maxwell's four relation and some derivation regarding the heat capacity, regarding the explanation of thermal expansion, anomalous behavior of water in the range 0 degree centigrade to 4 degree centigrade. We will discuss all these terms separately in the next lecture. Thank you.